Good morning and welcome to MiniLecture 12 on plotting derivatives. All right, so in the last lecture we talked about what a derivative means as the slope of the tangent line to a curve. In this lecture we're going to talk about some derivative rules that we use to take derivatives. We'll cover these rules in more detail in the coming lectures, and then we will talk about how to sketch a derivative by hand. All right, so let's start with those derivative rules. The first derivative rule is that the derivative of some constant c is equal to 0. So independent of what that constant is, 3, 2.2, negative 1.1, independent of what derivative we're taking, that constant is 0. All right, so the way to think about this is it actually follows from our definition of a derivative as the slope to a tangent line. So if this is our constant, say the constant 3, if we take the tangent line to this curve, it's going to be a flat line, and that's going to have a slope of 0, so the slope of the tangent line is equal to 0. All right, so the derivative of a constant is equal to 0. Now, if you have that constant multiplied by a function, so for example, the constant 3 multiplied by the function x squared, where we're taking the derivative with respect to x, then this 3 factors out, and we have 3, the derivative of x squared. All right, now, just like with limits, we also have rules for how to deal with sums and differences. So, if we take the derivative of the sum f of x plus g of x, and we take this derivative, we can split up that derivative on the sums. So remember that the derivative can be thought of as a limit. So just like with a limit, you can split things up on the sum. All right, so the derivative here can be split up into 3 different derivatives: d by dx of x squared, d by dx of 2x, and d by dx of 1. All right. Now, just like with the derivative of a sum, we can also split up a derivative on a difference. So there's actually a typo here. So if you have the difference between the functions f of x and g of x, that is also the difference of the derivatives, for the same reason that this is a derivative is a special type of limit, and so just like with a limit, we can split things up on a minus sign. All right, so over here we would have d by dx of e to the x minus, we can factor out that minus sign, d by dx of 2. All right, so those are some basic derivative rules. In addition to those derivative rules, we have a couple more. So first of all, we have the power rule. So if you have a function x to some power n, then you can take that n down and subtract 1 from it, and this will give you the derivative of that exponent. So if we do that over here, we're going to take this 3 down and subtract 1. So we have 3x squared. All right. Similarly, we have the derivative of a product and a quotient. So this is not as simple as the derivative of the sum and the difference. So we have to be a little bit more careful here. So first, starting with the derivative of the product, if we're taking the derivative of the product of 2 functions, f of x and g of x, we take the first function f of x times the derivative of the second, plus, note the plus sign here, plus the derivative of this first function times the second function. All right, so just to give us an example, imagine that we have x squared e to the x. So I've emphasized the multiplication here, but this might actually look something like that. So we have to intuit that there is a multiplication between this term and this term. All right, so what do we have here? Well, we have the first function, which is x squared, times the derivative of the second, plus the second function times the derivative of the first, like that. All right, now note that we actually have a special derivative, which we'll talk about much more later, that the derivative d by dx of e to the x is simply e to the x. So this is a special derivative. It's the only function where we take the derivative of it and we get back the same function. And so we can actually apply that and the power rule that we just talked about to actually reduce this further. So we have x squared. Now we take the derivative of e to the x. It's just e to the x. Now we have the second function e to the x, and then we're going to take the derivative of x squared. You guys just learned how to take the derivative of a power. If we have the 2, we're going to take the 2 down, and we're going to subtract 1. So we have times 2x. Note this is 2 minus 1 up here in the exponent. All right, so that is the derivative of a product. What about the derivative of a difference? All right, so we have to be a little bit careful because there's a plus sign here, and in the next one, in the derivative of a quotient, we're going to have a minus sign. So we do a very similar thing in the numerator, where we have the second function times the derivative of the first, but now we have a minus the first function times the derivative of the second, all over the square. So there's a little rhyme that goes with this, so low d high minus high d low, all over the square of what's below. So that is the quotient rule. All right, putting this into action, we have the second function, which is this function in the denominator, e to the x times the derivative, d by dx, of the numerator, minus the numerator times the derivative of the denominator, all over the square of the denominator, e to the x squared. All right, so we just learned some rules that we can reduce this further. So we have our denominator. Now, how do we take the derivative of x squared? You're going to take the 2 down and subtract 1. So you have times 2x minus x squared. Now, the derivative of e to the x is this special derivative here. And we have e to the x. Now we have the square of what's in the bottom. This is already a power, so we can combine this. So it's e to the 2x. All right. So that is the derivative of this quotient. Okay, so I know I'm going through these derivative rules pretty fast, but I just want to introduce them to you, and then we'll go over them one by one in the next lectures. All right, so there's one more that is going to be really helpful for us, which is the derivative of a composite function. And this is actually known as the chain rule. And so what do we have here? Well, we have that the derivative of f of g of x is equal to the derivative of the first function times the derivative of the second function. Okay, there's a typo here, it should be d by dx. And here, u is equal to g of x. So we first take the derivative of the first function with respect to some u, and then we plug in u equals g of x. All right, so that's a lot to handle here. So in order to see how this works, suppose we have the function a to the 2x. A to the 2x is a composite function of two other functions. So if we call this quantity here u, we have that a, if f is equal to a to the u, and u and g is equal to 2x, then a to the 2x is equal to f of g of x. All right. So to see how this plays out, we want to first take the derivative of this first function here. So we have d by du of a to the u times d by dx of g to the x, which is 2x. And then for this first function, we plug in u equals g of x is equal to 2x. All right, so to do this, we take the derivative of a to the u. We can use that power rule, so we're going to take u down and subtract 1. Note that we're taking the derivative with respect to u, and the u is in the exponent. So we have u, a to the u minus 1, times d by dx of 2x. So we plug in u equals 2x. Now, we can factor out this 2. The 2 comes out, and we have d by dx of dx dx. And this is simply 1. All right, so plugging everything in here, we have 2x, a to the 2x minus 1 times 2 is equal to 4x, a to the 2x minus 1. All right, that's pretty complicated. Don't worry about it. We're going to see it many, many more times. And so I just want to once again, I just want to introduce you to these concepts. So that's the hardest derivative rule. All right, now we have some special derivatives. I already told you guys about this one, that the derivative of e to the x is simply e to the x. And so if we have d by dx of e to the x over 4, that 4, we could rewrite this as d by dx of 1/4 e to the x. Now note that this is a constant, so it simply factors out. So we have 1/4 d by dx of e to the x, which is simply 1/4 e to the x. All right. Now, the derivative of the natural log of x is 1 over x, and you're just going to have to remember that. All right. So, similarly, if we have d by dx of 4 ln of x, that 4 factors out, and we have 4 times 1 over x. All right. So, 4 over x. Those are your derivative rules. All right. So now, how do we actually sketch the derivative of some function? So I've told you the derivative of a particular set of functions, but what if we have some function like this sine wave here? Now, we haven't talked about sines and cosines in this class, so how would we sketch the derivative of this function without actually knowing how to take the derivative? All right, so there's actually 3 simple rules for doing this, and the first step is to find the turnaround point. So we want to find the points where the function changes direction. And note, if we take the tangent line is going to be flat here, and so the derivative is going to be 0. So we first find these derivatives equal to 0, and we draw them at 0 here on our plot. So we have something like that. All right, now you're going to identify the regions where the derivative is positive and when the derivative is negative. All right, so to remember whether the derivative is positive or negative, we're thinking about the slope. So imagine like a little bicyclist. If the bicyclist is going uphill, then it's a positive derivative. If the bicyclist is going downhill, then it's a negative derivative. So this is a positive region. This is a negative region. This is a positive region. This is a negative region. This is a positive region. Note that it should switch sign at each one of those turnaround points. All right, so now we know that over here is going to be positive, this is going to be a negative, this is going to be a positive, this is going to be a negative, and this is going to be a positive. So we know our derivative is somewhere up here, then down here, then up here, then down here, then up here. Now the next part is maybe the most vague, and that's okay. We're just trying to sketch here. We're just going to guess the magnitude. So think about how steep that bicyclist is going up. Here it's going up really steep. Here it's like slowing down and it's getting less and less steep. So we have something like it's really steep here and it slows down. Then it gets really steep as it gets here and it slows down. So we have small, it's barely going downhill. Now it's going downhill a lot and then it slows down. All right, here it's just barely going uphill, and then it's going uphill faster, and then it gets closer to the top of the mountain. All right, so we're gonna just sketch. Oops, that should go through there. So as you note, these are very vague plots, but they give you a general sense of what the derivative looked like. Now, I didn't do a very good job here. This wouldn't pass the vertical line test, so this isn't actually a function, so it should be much more like that. All right, so that's how you sketch a derivative. And with that, I'm going to leave you with the self-study question about osmosis, where you're going to use some of those derivative rules. Just look them up and apply them at this moment. We'll go over them in more detail, and you're going to try to sketch the derivative of this function v of p. All right, take care. Bye.